Azide is the anion with the formula N3-. It is the conjugate base of hydrazoic acid. N3- is a linear anion that is isoelectronic with CO2 and N2O. Per valence bond theory, azide can be described by several resonance structures, an important one being N- equals N plus equals N-. Azide is also a functional group in organic chemistry, Rn3. The dominant application of azides is as a propellant in airbags. Preparation. In organic azides, sodium azide is made industrially by the reaction of nitrous oxide, N2O, with sodium amide in liquid ammonia as solvent. N2O plus 2NaNH2 NaN3 plus NaOH plus NH3. Many inorganic azides can be prepared directly or indirectly from sodium azide. For example, lead azide, used in detonators, may be prepared from the metathesis reaction between lead nitrate and sodium azide. An alternative route is direct reaction of the metal with silver azide dissolved in liquid ammonia. Some azides are produced by treating the carbonate salts with hydrazoic acid. Organic azides. The principal source of the azide moiety is sodium azide. As a pseudo-halogen compound, sodium azide generally displaces an appropriate leaving group to give the azido compound. Aryl azides may be prepared by displacement of the appropriate diazonium salt with sodium azide, or trimethylsilyl azide. Nucleophilic aromatic substitution is also possible, even with chlorides. Anilines and aromatic hydrazines undergo diazotization, as do alkylamines and hydrazines. Appropriately functionalized aliphatic compounds undergo nucleophilic substitution with sodium azide. Aliphatic alcohols give azides via a variant of the Mitsunobu reaction, with the use of hydrazoic acid. Hydrazines may also form azides by reaction with sodium nitrite. PHNHNH2 PHN3 alkyl or aryl acyl chlorides react with sodium azide in aqueous solution to give acyl azides, which give isocyanates in the Kirchhoff rearrangement. The azo-transfer compounds, trifluoromethanase sulfonyl azide and imidazole 1-sulfonyl azide, are prepared from sodium azide as well. They react with amines to give the corresponding azides. RNH2-RN3 Dutt-Wormel reaction. A classic method for the synthesis of azides is the Dutt-Wormel reaction, in which a diazonium salt reacts with a sulfonamide first to a diazoaminosulfonate and then on hydrolysis the azide and a sulfonic acid. Reactions. Inorganic azides. Azide salts can decompose with release of nitrogen gas as discussed under applications. The decomposition temperatures of the alkali metal azides are NaN3, KN3, RBN3, and CSN3. This method is used to produce ultra-pure alkali metals. Protonation of azide salts gives toxic hydrazoic acid in the presence of strong acids. H++ N3- HN3 azide salts may react with heavy metals or heavy metal compounds to give the corresponding azides, which are more shock-sensitive than sodium azide alone. They decompose with sodium nitrite when acidified. This is a method of destroying residual azides prior to disposal. 2NaN3 plus 2HNO2 3N2 plus 2NO plus 2NaOH. Many inorganic covalent azides, e.g., chlorine, bromine, and iodine azides, have been described. The azide anion behaves as a nucleophile. It undergoes nucleophilic substitution for both aliphatic and aromatic systems. It reacts with epoxides, causing a ring opening. It undergoes Michael-like conjugate addition to 1,4 unsaturated carbonyl compounds. Azides can be used as precursors of the metal nitrido complexes. Azide complexes thus is induced to release N2, generating a metal complex in unusual oxidation states. Organic azides. Organic azides engage in useful organic reactions. The terminal nitrogen is mildly nucleophilic. Azides easily extrude diatomic nitrogen, a tendency that is exploited in many reactions such as the Staudinger ligation or the Curtius rearrangement, or for example in the synthesis of gamma-amino beta and amino esters. Azides may be reduced to amines by hydrogenolysis or with a phosphine, e.g., triphenylphosphine, in the Staudinger reaction. This reaction allows azides to serve as protected NH2 synthons, as illustrated by the synthesis of 1,1,1-triethane, 3H2 plus CH3C3CH3C3 plus 3N2 in the azide alkene Huish-Gent cycloaddition. Organic azides react as 1,3-dipoles, reacting with alkenes to give substituted 1,2,3-triazoles. This reaction is very popular in click chemistry. Another azide regular is tosyl azide, here in reaction with norbornadine in a nitrogen insertion reaction. Applications: about 250 tons of azide-containing compounds are produced annually, the main product being sodium azide. Detonators and propellants: sodium azide is the propellant in automobile airbags. It decomposes on heating to give nitrogen gas, which is used to quickly expand the airbag. 2Nan3 plus 3N2 heavy metal salts, such as lead azide, Pb2, are shock-sensitive detonators which decompose to the corresponding metal and nitrogen. For example, Pb2 Pb plus 3N2 silver and barium salts are used similarly. Some organic azides are potential rocket propellants, an example being 2-dimethylaminoethylazide. Other because of the hazards associated with their use. Few azides are used commercially, although they exhibit interesting reactivity for researchers. Low molecular weight azides especially are considered hazardous and are avoided. In the research laboratory, azides are precursors to amines. They are also popular for their participation in the click reaction and in Staudinger ligation. These two reactions are generally quite reliable, lending themselves to combinatorial chemistry. The antiviral drug zidovudine contains an azido group. Some azides are valuable as bioorthogonal chemical reporters. Safety: azides are explisophores and toxins. Sodium azide is toxic, equals 27 mg per kilogram, and can be absorbed through the skin. It decomposes explosively upon heating to above 275 degrees Celsius and reacts vigorously with CS2, bromine, nitric acid, dimethyl sulfate, and a series of heavy metals, including copper and lead. In reaction with water or Bronsted acids, the highly toxic and explosive hydrogen azide is released. Heavy metal azides, such as lead azide, are primary high explosives detonable when heated or shaken. Heavy metal azides are formed when solutions of sodium azide or HN3 vapors come into contact with heavy metals or their salts. Heavy metal azides can accumulate under certain circumstances, for example, in metal pipelines and on the metal components of diverse equipment, and thus led to violent explosions. Some organic and other covalent azides are classified as highly explosive and toxic. Inorganic azides as neurotoxins, azide ions as cytochrome C oxidase inhibitors. It has been reported that sodium azide and polymer-bound azide reagents react with dichloromethane and chloroform to form di- and triazidomethane, RESP, which are both unstable in high concentrations in solution. Various devastating explosions were reported while reaction mixtures were being concentrated on a rotary evaporator. The hazards of diazidomethane have been well documented. Solid iodoazide is explosive and should not be prepared in the absence of solvent.